Good afternoon, everyone, and welcome to Epic eLearning web class. Before I move forward, can you please confirm with you? Can you hear me properly? Is there sound, audio quality good? So you'll see there is a chat box on your right side corner. So yeah, if you need to interact with me, just type your comments on the chat box. I already got one comment from Mr. Noor Aziz. I said yes, I can hear you properly, so good enough to hear. So yeah, so thanks to know the comments. We are now ready to start. Okay, all right. Okay, today what we'll be doing the routing basic e-learning presentation. So when I'm saying routing basics, so definitely we'll be discussing about the basic knowledge that we need to know when you need to kind of go further detail of the IP routing. Okay, so yeah, so we'll be discussing about the very basic concept of IP routing. Let's go forward. Okay, I'm your presenter today. My name is Nurul Islam Roman. My role is as a technical training officer in Epic. So yeah, I usually kind of deal with the technical training delivery in Epic. I have joined in Epic in 2006, so as an internet resource analyst, and I worked as 3 years since after I joined as internet resource analyst. In 2009, I have moved into the training role, and that's what I'm doing now. So my specialization is on obviously the routing and switching, then IPv6, DNSSEC, Internet Resource Management, and network security. So if you have any question, like when we will be presenting today, so yeah, definitely we'll be discussing about the basic routing. Yeah, and then if you have any question on that, you can ask me anytime. Okay, so we have an FAQ section here. So if you go to www.epinic.net/elearning support, then you'll see the common issues that you might face by when you're using this platform, e-learning platform. So it's worth having a look if you face some difficulties using that the software platform that we're using today. And then afterward, when you finish the presentation, we expect you put a feedback, or send us the feedback. So we have an URL to send us the feedback. So at the end of the presentation, I will show you that and how you can send us the feedback. So lastly, I would like to acknowledge Cisco assistance, because when we prepare the presentation materials, we actually use lots of Cisco's presentation or the concept or knowledge in this presentation. So thanks to them. Okay, so what does a router do? Right. So the question is, what does a router do? Obviously, the answer would be learn or find paths, and then afterward, when they finish finding the path, keep forwarding the packet. Just forward the packet. That's what their job. And when they're forwarding the packet, parallelly at the same time, they'll also try to see the path they learned before still valid or not. If it's not valid, or if it's no more available, then find the alternate path and then forward the packet. So most of the job that router does forward the packet, and as well as they need to learn the routes as well, right, or the paths as well. So that is what the basic job of a router: finding the path and then forward the packet when it comes to an IP routing concept. So yeah, so when you need to learn routing, what you need to learn as a router: how they learn paths, how they learn alternate path, and how they forward the packet. That's it. Okay, so this is what we need to learn. So we'll be discussing about the basic concept of the functionalities of a router: finding the path, forward the packet until switch on or powered off. Okay. Routing versus forwarding. So when we need to deal with the routing, or if you come to the routing concept, you will face those two terminology, routing and forwarding. So what is the difference between routing and forwarding? So in very basic, routing is kind of a process that will help the router to kind of build the map of the whole topology. When I'm saying the topology, it means when the routers are internally connected, right? So there will be a sort of physical connectivity in between routers to forward the packet, right? So when the routing protocol works on the router, the function of a routing protocol is kind of to build the topology map, how it is physically connected, and then afterward, how or what are the destination network available within this physical network and how to reach those. Is there only one path or more than one path? Learn all those information and then afterward find the best path and install the best path into the routing table. So when it goes to the routing table, then router need to kind of build a sort of table inside. So for example, we call it a kind of MAC table, and by using that MAC address table, and then the port is connected to, so they start forwarding the packet. So that is why routing is kind of a function that helps the router to build a map of the topology and learn the networks or destination that they have, and then by learning all those, router might have more than one path to the same destination. Then they build a forwarding table. That forwarding table is only within the router to kind of build a map of which interface of that router will be used to send the packet to that particular destination. That's what we call the forwarding table. And in forwarding table, we all have all the time, the interface, MAC address, and the destination address mapping. That's it. Okay. All right. So the function of IP routing, or what is IP routing? So IP routing is finding the path. So that is what the function, the core function of the router, finding the path. So how this information actually learn or derive by a router, right? Finding the path. So when those routers are internally connected, after the physical connectivity, they kind of build a relationship among all those connected routers, right? We call it sometimes neighbor relationships. So when that relationship has been built, that can be built automatically or that need to be built manually, right? It depends on the routing protocol. So when the neighbor relationship has been built among those routers, right, or peering relationship, after this neighbor relationship or peering relationship, they actually start exchanging the connected networks they have or the networks they have learned from the other neighbors. So this is how they exchange the routing information among those connected routers, right? So when they learn all those route among the connected routers, from those route to a single destination, there might be more than one path, because the topology, if you see the topology, the connectivity among those routers, there can be multiple connection, multiple paths to go to the certain destination, right? So this is how router knows, yes, there are more than one path to certain destination. When there are one path or more than one path to certain destination, then the job of an IP routing protocol is to find the best path at that particular time, right? So the best path at that particular time will be installed in the routing table, and all other suboptimal paths will be in another table, like topology table on the router. Then this is how router keeps sending packet. If the best path are no longer available, then they go and install the next available best path, which are already in the topology table, right, and put that things as the best path in the routing table. So that is what the function of a router. So when they build that topology table or the best path, right, into the routing table, that is not the end of the job. They also need to maintain it, right? As I said, router need to maintain the path as well. So that path maintenance function can be periodic or topology change or trigger driven. So for example, if there is any topology change on the network, right, then that router who identified the topology change can initiate a trigger update. So this is how all the other neighbor can know or might know there's a change on the network, right? And then they start building their table, or they start kind of finding an alternate route from the topology table. So that is how router maintained their routing table, either periodically or as a topology change happen. It depends on the type of routing protocol, or it can be a combination of both. Then router need to decide which path is the best path if router has got more than one path to the same destination. So to select the best path, router can use a number of unit to select best path. So the number of unit, or the unit that router used to select the best path, we usually call them metric, right? So metric can be hop count, it means how many hop away, right? Metric can be on a combination of so many factors like bandwidth, delay, MTU, and so many things, sometimes filtering as well. Okay, all right, let's move on. IP route lookup. So when router look up the best option or best path to a destination, there's a very important concept that we need to remember is the longest prefix match. So who works on IP routing, who has got the basic understanding of IP addressing, right? So if you see how routers select the best path from the available path options, router always use, or the routing protocol always use the longest match routing. What does that longest match routing? We have an example in here. Say for example, I have a packet. That packet destination is to a network called 10.1.1.1/32, right? It's a unique address, or to that address the packet needs to be sent. When that packet comes to any router, right? If the router has got network to that destination, say for example 10.0.0.0/8 and 10.1.0.0/16. So right, we have two match in the routing table, right? That destination 10.1.1.1/32 can be a part of 10.0.0.0/8, or it can be a part of 10.1.0.0/16. Both destination can be a match. Then which outgoing interface the router can be used to send the packet to? The very common logic on a router is the longest prefix match. Longest prefix means number of bit, longest bit match. Say out of 8 bit and 16 bit, 16 bit is the longest because the bigger number. So that's why 10.1.0.0/16 would be the best match to send the packet to. Okay, let's have a look. We have more example on that one. Say on that topology, we have router 1, router 2, router 3, and router 4 is connected in that topology. So there is a packet, there is a request actually came. Oh, just a second. Okay, a request actually came from router 1. The packet came to router 2 for a destination of 10.1.1.1. So when that packet goes to the router 2, and router will go and have a look into this routing table, where is the match? If you see the routing table on R2, there is a network called 10.0.0.0/8, and that network is reachable via router R3. And 10.1.0.0/16, that network is reachable via R4. So what does that mean by reachable or reachability? So in here, router R3 and R4, in here, router R3 and R4, they actually announce that prefix from their network. So for example, router 3 has announced 10.0.0/8 from their network, and router R4 has announced 10.1.0.0/16 from their network. When they start announcing it, so that announcement comes to R2, same announcement comes from R3 on a different prefix length, right? So this is how R2 knows to go to the destination 10/8, the next stop is R3, and to go to the destination 10.1/16, the next stop is R4, right? So when the packet is, the request came from the other side of the network, they will have a match on this routing table. So if you see the match, so when they're trying to have a match on the existing routing table, so that destination, what the router will do initially on its routing table, what is the prefix length /8, right, will be having an AND operation with the destination address. So prefix length of this routing entry and the destination packet, there is an AND operation, right? And that network that already has got plus their prefix, there's AND operation. If both are matched, it means there is a match for that destination, right? So here we have a match. Then it goes to the second entry, 10.1, same operation but different prefix length. So 10.1.1.1 FF, which is /16, and then entry 10 and then /16. Again, there is a match. So we have two match. Then which match will win? As I said in the previous slide, longest prefix match. So in here we have the longest prefix, which is 16-bit. So that will be used as a next hop. So from router 2, this packet will be forwarded to R4. Make sense? For other two entry like 20 and 30, definitely there is no match, because 10.1.1.1 and /8, 20.0.0.0/8, there will not be any match in the AND operation. With 30, and obviously there will not be any match with destination 30 as well. So those two are invalid match, and we have two valid match. Out of two valid match, longest prefix match will be winning. Make sense? So if you have any question, you can ask me anytime. So you don't need to wait till the end of the presentation. You can ask me if you have any question anytime when I'll be doing the presentation. Just send your question on the chat box. I'll try to see your question and try to answer as quickly as I can. All right, so let's move on, please. On the next slide, we have a discussion on RIB and FIB. RIB stands for Routing Information Base, and FIB stands for Forwarding Information Base, right? Or forwarding table. What does that mean by routing information base or routing table and forwarding information base or forwarding table? Let's discuss about the routing information base or routing table. So in the routing table, what a router usually contains a list of all destination. So what are the destination that we have within the network, right? A list of all those, and the next hop, who will be the next hop. And next hop is most of the time the next hop router's interface, so which interface will be used and the IP address of that. So that is how router maintain the routing information table, right? And the next hop can be a number of, to go to the same destination, we might have more than one next hop, right? It could be based on the routing protocol that we're using. But in the forwarding table, what the router maintain, the next interface within the router to reach to a certain destination, what will be the interface or which interface will be used within this router to go to the next hop, right? So that is what we maintain, or the router maintain in the forwarding information base or in FIB. Some people, still they call routing table, the FIB as a routing table, or the route. Probably, to be specific, FIB is the forwarding table and RIB is the routing table. And if I summarize, RIB or routing table contain the destination and the next hop, and next hop can be a number of, and it can be kind of an address of another router, right? Next hop can be an address of another router or the connected router, right? Or sometimes it can be a router that is remote within an AS. So for example, like the loopback address of another router, if I consider IBGP, right? So in routing information base or RIB destination, and the next hop can be an IP address of any router. It can be the local router, it can be another remote router. But FIB or forwarding information base is destination and the interfaces that the router need to use, right? So that is what the difference between RIB and FIB. Any questions so far? Okay, now we'll explain or we'll discuss about the explicit routing versus default routing. So what does mean by default routing? What is default, right? So default routing is, say for example, if you are an enterprise, small organization using internet for your daily, operations, so email, accessing web and all sort of things, you have a small router into your network and that connected to the ISP, right? So for that reason, you can only buy a very small router, like small Cisco, Juniper, or whatever, the router that you can afford or think is useful for you. So on that router, if you want to browse any site of the internet, say Google, Yahoo, XYZ, Epinic, whatever you want to browse, right? That all requests go via that router and then the next ISP. So there's only one path to go to the internet, right? So if there's only one path to go to the internet, right? So we don't need to know every destination in the world. So for example, from Brisbane, where I am in now, if I need to go to say any suburb in US or any suburb in UK or a suburb in Switzerland or in suburb in somewhere in say Egypt. So everywhere, if I need to go, what is my option? From here, I have to go to the local airport, and from there, I need to fly. So if you see the destination that I have in the world, so what I can have in my home, everywhere in the world, go to the Brisbane airport. So by adding a single route into my routing table, I can go everywhere in the world, right? So it's very easy for me because to remember a single route, select everywhere. It's very easy, simple, and I don't need to think a lot. So my CPU use, memory use is very minimum to learn only one route everywhere. Go to the Brisbane airport. That's what we call default route. Explicit route. What does that explicit route means? Explicit route means you need to know every destination in the world. How to go to Japan, a single suburb in Japan, or a suburb in Korea, or a suburb in China, right? So I need to know every individual address, and then I can plan how I can go. Say for example, if I have got more than one path, say for example, I can go via Brisbane airport, or I can go via Brisbane seaport, or I can go via any other destination, any other option that I have in Brisbane. So if I have got more than one path, then I need to calculate, okay, if I need to go to Japan, which path I should use? If I need to go to US, which path I should use, right? So this is called explicit route. So every available destination that we have in the world, I have in my mind, all the addresses that I have in my mind. And I know which path is the best path to go to the destination. That's what sometimes we call default free zone. We don't have any default. Default means if any request come to go to any address and that address doesn't have any match in my mind, I'll just discard the packet. No, I don't have any destination. Discard it. That's what we call explicit routing or default free zone. And then hybrid. Hybrid is a kind of a combination of default plus some number of route. So what does that hybrid means? Hybrid means, say for example, I have got explicit information about the regional destinations within Asia Pacific. The rest of the world, I just use my default route. So it can be a hybrid routing. So the benefit of default route is very simple, very cheap, easy to manage. But the downside of it is I don't have much granularity in terms of selecting the path. Only one path, doesn't matter how far or how close it is. Explicit, the benefit is I have exclusive information. I can calculate which way is my best path. Very kind of granular in terms of selecting my best path and then the options. But in terms of managing it, it takes high overhead, very complicated. costly, and obviously CPU intensive. So yeah, so every option has got upside and downside. Hybrid, you need to have some filtering knowledge. Filtering knowledge means like you need to check uh, to go to regional network, this is what the path, and to go to the other side, this is what the path. We have to make some filter in it. So that is what some upside and downside of all those possible options. Okay. Now we'll discuss about egress traffic. Egress traffic is, I'm talking about traffic. Egress traffic is how the traffic will leave from your network, right? How the traffic will leave from your network. When the traffic will leave from your network, say for example, the analogy that I gave, from my office, I want to browse www.google.com. When the packet goes to my router, right, and from the router it goes to the internet, that's what we call egress traffic, traffic going out, right? So if I need to ensure traffic goes out, what are the preconditions that we need to match on the router? To ensure the traffic can go out, or egress traffic, right, we need to have the route available on the routers. We need to have the route available on the routers. So for example, www.google.com, the request goes to the router. When router need to forward the traffic outside, they need to know how to go to Google, right? They need to know their address. From where the address will come? From outside, the announcement will come. So if you see the egress traffic, to send egress traffic out, routing announcement should come outside and come to the router. So that's what we call route availability. So to ensure the egress traffic, you should have the route within your router. Then acceptance. So when someone sends that route from outside, say for example your ISP, Google route, to your router need to accept it. If your router don't accept it, then how come that route will be available on the routing table? So router need to accept it. Then afterwards, some policies and tuning. If we have any policies, complicated policies, like to send traffic to Google, this is the path. To send traffic to Yahoo, that is the path. If you have that sort of policies, I'll explain the policy later on, like we have some slides. But as of now, if we have any policies, that will also need to match. And if the policy match, then only your router will accept the route, and then only the egress traffic can go out, right? That depends on the peering and transit agreement. So if you have kind of a peering agreement with your service provider or with any of the organization, and through peering agreement you exchange the local route. So he will send you the local route, you send him the local route. So when you send the local route, then egress traffic only can go within the local network. They cannot go outside. If you have a transit agreement with your upstream, right, the benefit is transit means everywhere in the internet you want to go, you can use them as a transit, then go to the destination. So if you have a transit agreement, egress traffic can go. If you have a peering agreement, local traffic as an egress traffic can go. Okay, so these are the preconditions that need to match. Ingress traffic, which is other way around, traffic coming from outside to your network, that's what we call ingress traffic. Same way, to ensure the ingress traffic can come into your network, you need to ensure you're sending your route to the outside based on your addressing. So whatever the prefix that you have, right, if you send your aggregated prefix, so every part of your network people can come in. If you send only specific prefix, only for that specific network traffic can come in. So that's what depends on the ingress traffic. Autonomous system, AS. What is an autonomous system? By definition, an AS or autonomous system is a collection of routers. Is a collection of routers under a single routing policy and under a single administrative control. It means if you see on the diagram, we have 5 routers, all the 5 routers connected in that topology diagram. All those routers are administered by a single administrator. He has got access to all the routers, and all the routers are having the same routing policy. Routing policy means in terms of selecting best path within the network. They are sharing the same routing policy. They all trust themselves. So all the routers, since they belong to the same AS, whatever the announcement, advertisement coming from the other side, they all trust themselves, right? So in an autonomous system, if you see the routing behavior, routing can be done within an autonomous system. In this case, within all those 5 routers, select the best path. Routing can be done in between autonomous system. If there is another autonomous system, we can do routing in between autonomous system. So if you see the internet has been built by interconnecting a number of autonomous systems. If you see the number of AS that we have, nearly 50,000 AS currently. So all those ASs are interconnected. So when we do routing within an AS, right, all the routers, they group their routing announcement using a number called autonomous system number or AS number. Okay, those are under same administrative control, same ownership, trust. Okay. Some definitions of terms in routing. Say neighbors. What does it mean by neighbor in terms of routing? So neighbors, definition of neighbor is, if you see within the autonomous system, all those routers, if they share the routing information, right, they all are neighbors. They're connected. They have to be connected. So directly connected routers, when they share the information, routing information, they are all neighbor. Or when you consider about AS, right, two directly connected routers in between AS, they also can form a neighbor relationship and they can exchange routing information. Announcement. What does that mean by announcement? Announcement means a router send routing information to their neighbor. When the router sending the routing information to their neighbor, right, that information the router sending, he can learn from another neighbor, right, or it can be his own route. So he's announcing it to his neighbor. Except, what does that mean by except? Except means when a neighbor send any routing advertisement, the neighboring router, they accept that advertisement. That's what we call accepting. And they can use it in their routing table for further processing. Originate. Originate means any router, they are inserting a route into the routing table through IGP, right, or through a network statement. That's what we call originate. There's a little bit different between announcement and originate. Announcement is forwarding the announcement to the other side, and it can be learned from another neighbor, not necessarily the router is originating it. And originate means the router itself actually originate that announcement. The router itself actually originate that announcement and send it to the neighbors. So that's the difference between announcement and originating. Any question? Then we have the definition called PR, right? PR means a sort of neighbor relationship in between routers, right? When those two neighbors, they send or they exchange routing information and they build a peering relationship. So in terms of business definition, peering relationship in between two neighbors is actually exchanging routing information without any fees. There is no business relation. They are just exchanging routing information in between. That's what we call PR or peering. Okay. Routing flow and packet flow. So this is another sort of concept that we need to be very much clear about to understand the routing. When we see two AS, AS1 and AS2, they need to exchange traffic or data packet. There has to be a precondition that already been accepted before they start exchanging the data. What are the preconditions? So for example, AS1 on the other side, on my left hand side I have AS1, and on the right hand side I have AS2. If AS1 and AS2 they want to communicate or they want to exchange data, then AS1 first must announce its prefixes to AS2. So AS1 must announce its prefix to AS2 first, right? So AS1 will announce prefix to AS2, AS2 must accept the prefix announcement. When it accepts it, then to have a two-way communication, AS2 must announce its own prefix to AS1 again. When the announcement goes to AS1, AS1 need to accept it. So when that precondition has been matched, then traffic can flow in between, right? So if you see the traffic pattern and routing pattern, so the precondition is AS1 must send the routing announcement in this direction, routing announcement this direction, then traffic can come on the other way around. It's like if I am inviting you to come to my home tonight for a dinner. So you're the traffic, you're coming in my home tonight for a dinner. Then what I need to do? I have to send my home address to you. So if I send my home address to you on this direction, then you as a traffic can come other way direction. That's what we call routing flow and packet flow. Routing flow and packet flow are opposite directions. So if the routing flow on this way, packet can come other way. Makes sense? All right, so let's move on. So routing flow and packet traffic flow, that's what I was explaining. In terms of policy language, if we filter outgoing routing announcement, so it means I am filtering my outgoing routing announcement, it means I'm not sending my home address to you, then it inhabit traffic flow inbound direction. If I don't, or if I filter my home address to you, then you cannot come to my home for dinner. So filtering outgoing routing announcement will inhibit incoming traffic flow. Same way, filtering inbound traffic routing announcement will inhibit outbound traffic. Right? It's very simple. Okay. Now we'll see routing flow and packet flow with multiple AS. In a situation when we have more than one AS, how routing flow and traffic flow will be happening. In here, we have an AS called AS1, right, who is originating a network called N1 that connects to an AS called AS34 that connects to another AS called AS8, and then AS34 and AS8 are internally connected, and then AS8 is connected to AS16, and AS16 is originating a prefix called N16 or network 16. So in a multiple AS environment, right, if we need to see in multiple AS environment how traffic flow and routing announcement works. Say for example, from AS1 for network N1 in AS1 to send traffic to network N16 on AS16. So our requirement in here is network N1, which is on AS1, want to send a traffic to network 16 on AS16. Right? How these things can be achieved in the routing policy or in the routing system. AS16 first, AS16, they first must originate and announce network 16 from AS16 to AS8. And then AS8 must accept it. So if you see the control, first control is in here. Which direction? Outbound direction of the routing flow. So from AS16, if the announcement of network 16 is allowed in here, then that announcement can come on AS8. And then there is another control in here on AS8. How? AS8 can accept it or discard it, right? But in our analogy, if we need to do this, then AS8 must accept that announcement of network 16 from AS16. When it accepted it, then after what is the next? AS8 then need to forward that announcement to the AS1, When it goes to AS1, that announcement goes to AS1, then the traffic condition has been achieved one way, one direction. And to have a return traffic, N1 from AS1 need to go to AS8 now, and AS8 need to forward it to AS16. Again, the same concept, in filter, out filter need to be matched or need to be accepted. So in that case, if the routing announcement happen from the both way, from AS16 up to AS1, then traffic can go in this direction, If traffic need to come through or via other direction like this, then what are the precondition? Then AS8 need to announce that prefix announcement to AS34 as well, and then AS34 need to announce it back to AS1, right? So if those two As cooperate with AS1, then only AS1 will have two paths to go to the destination, via this path or via this path, and for that definitely AS8 and AS34 both need to cooperate. Make sense? So this is how the routing flow and packet flow will influence in multiple AS environment. We have more diagram, more analogy. So let's see, policies can be implemented in more complicated way. So routing policy is a sort of policy that is actually used to control the traffic flow in and out of an ISP network. So routing policy is sort of a policy that is used to control traffic flow in and out of an ISP network. Okay, so ISP makes decision on what routing information to accept and discard from its neighbor. So when ISP, they need to take the decision of which routing information I should accept from neighbor, which routing information I should not accept from neighbor, right? That depends on a number of factors. What are the factors? Okay, the very common one is the individual route. So when two ISPs, they accept prefix, they can accept prefix based on individual routes, right? So when they work on individual routes, if you see in the world, the routing table in IPv4, we have more than 400,000 prefixes. So in terms of scalability, to deal with 400,000 individual prefixes is not an easy job, right? So that's why we have a number of options, right, to deal with a number of prefixes. So that routing policy can also work based on originated by specific AS, and AS can originate more than one prefixes, right? 10, 25, 6, whatever number of prefixes an AS can originate, right? So this is how we also can create route filters based on the origin AS, or the based on via which ASs the prefixes are coming, right? Like any prefix announcement originated in US coming via an ISP in UK, then via another ISP in Italy, and then afterwards, say for example, China, then Japan, then all the way to Australia, right? So this is how you also can create the routing policy based on filters, based on the routes or the AS that routes is being traversed. We usually call it AS path filters simply, or routes belonging to a group, right? It means routes, when a number of routes has been originated by different ISPs, a single ISP can group all those routes using a grouping number or tagging number. We usually call it PGP community. Using community, we can group routes, and based on the group, we can create the filters. Make sense? So this is how we can have some sort of scalability in terms of handling huge number of available routes in the global internet. Make sense? Is there any question before I move forward? Okay, now we have a complicated, not complicated, but advanced slide on the policy. So for example, in here, we have an AS called AS99. It is connected to the internet using a link called red link. Another one is a green link, right? So the requirement is any traffic or the network on the other side of the internet called red network, if the traffic from red network need to come to AS99 via the red link, and traffic or all the other traffic on the green network will come via the green link. If the AS99 need to implement this sort of policy, how AS99 can do that? So to do this sort of policy on AS99 or to implement this sort of traffic engineering in AS99, so what AS99 need to do? They need to accept route originated from the red AS, all the route originated from the red AS via the red link. If the network originated from red AS comes via the red link and all and this router AS99 has accepted that networks in the red AS via the red link, then only packet to the destination of red network or red AS can come or go via the red link, and rest of the traffic, right, originated in other side, green AS need to forward those to AS99 via green link, right? When rest of the prefix or rest of the destination, green AS send to AS99 via green link, then on the rest of the world, AS99 can go via the green link. That is what sort of a limitation of the routing. I mean, it's not a limitation, I would say. It's sort of a policy limitation. So this is how we can control the routing system in the internet and implement the business policy. Make sense? Any questions so far? Okay. Now we will see more complicated one. So now we have another AS in the middle called AS22, in between red AS, green AS, internet, and AS99, right? So AS99 would like packet coming from the green AS to use the green link. Packet coming from green AS to the green link, right? If AS99 want to achieve this, packet coming from green link, green AS would come via the green link. So what the green AS will do, green AS will forward that announcement to AS22 in the middle. If AS22 send or forward that announcement to AS99 via the red link, then AS99 cannot achieve that goal. Sending traffic to green network or green AS via green link, no, it will go via red, because since AS22 hasn't cooperated. If AS22 cooperate AS99, and when AS22 receive that prefix announcement from green AS, forward that to AS99 via the green link, then only AS99 can get packet or traffic from green network via the green link. Make sense? So if you see the building block of internet, a number of AS, so between your AS and your destination, all the AS in the middle need to cooperate if you need to do some sort of traffic engineering, right? So yeah, those are the basic of implementing routing policies. Now if you see the routing protocol, in terms of routing protocol, there are a number of class of routing protocol. So simply we have two different class, IGP and EGP. IGP stands for Interior Gateway Protocol, right? So what does that mean, Interior Gateway Protocol? Interior Gateway Protocol, or the class of routing protocols actually used to do routing in between, within the AS. Within your AS, if you have a number of routers, right, and they are connected in a redundant topology, and if you have more than one path, so in between within the AS, if we need to do routing within all those routers, IGP class of routing protocol can be used. The example of our IGP class is, say for example, WESPF, ASes for the service provider network, EIGRP, RIP probably for the enterprise network. Then the second class of routing protocol that we have called EGP, or Exterior Gateway Protocol. Exterior gateway protocol is sort of a routing protocol that actually used to do routing in between two AS or in between two different ISP. That's what we call exterior gateway protocol. If you see the interior gateway protocol and exterior gateway protocol, interior gateway protocol actually used to select the actual best path based on the topology, and eBGP, when they select the best path, they actually select best path based on the business policy in between two AS. What is the business relation, right? They don't really look into the very nitty-gritty of selecting the actual best path. They always rely on the business policy or the policy part of the selecting the best path. So interior gateway, as I said, this sort of routing protocol actually used to do routing within an autonomous system, right? And if you see the IGP class of routing protocol, they really carry the infrastructure prefixes within that autonomous system. Infrastructure prefix means that includes, obviously, the first infrastructure prefix is the loopback of all those routers, right? And then the point-to-point link within the ISP, say for example, infrastructure point-to-point link. Those are actually like announced on IGP, class of routing protocol. Since IGP, they use sort of an algorithm to select the best path, and they maintain a topology table. And the way IGP works, we always try to make sure our convergence times, it means quickly the routing table can be converged to start forwarding packet, will be as less as we can, or as less as the convergence time. It is much better. So that is why within an IGP protocol, most of the service provider, they only announce the infrastructure prefix. So they don't want to grow the IGP table. If you announce other than infrastructure, say for example your customer prefix, then your IGP will be growing too fast, and when it is growing, you can't scale because IGP cannot handle hundreds of thousands of routes the way BGP handle it. That is why we always try to ensure we announce our infrastructure in IGP, and this is how all those routers are reachable via IGP, and then afterward external prefix can go via PGP or EGP protocol, EDP type of protocol. So then IGP will use as a next hop of PGP. That's it. So as an IGP protocol, the option that we have within the industry, WESPF and ASes. WESPF has got two versions, version 2 and version 3. Version 2 support only IPv4, version 3 support only IPv6. If you need to have a dual stack router, both version 4 and version 6 of IP, you need both WESPF version 2 and version 3. And WESPF only works on IP, IPv4 and IPv6. Then we have the other option called ASes. ASes is a sort of routing protocol. They support multi-protocol, right? AppleTalk, IP, IPv6, all this support. So if you have, or if you're running a kind of a multi-service platform, ASes can be an option for a service provider. If you're running only IP, probably WESPF is a good option for you. We can see WESPF is very popular. We have so many WESPF kind of expert people around. But ASes in terms of WESPF scalable, but we don't see that much of expert of ASes around the world if you need to hire someone. Alright, so this is what we have on IGP. Then we will discuss about what or why do we need an IGP in the infrastructure. So as I said, IGP are used for your backbone scaling, right? So if you have kind of a hierarchical backbone, so you have your regional network, topology, POPs, and all sort of other things. So we have IGP. So that will limit the scope of failure. So within your infrastructure, if you have more than one link, IGP will ensure the we reach the other part via the alternate path. We only announce the infrastructure prefix, as I said, and design goal is to minimize the prefix in IGP so that it can scale and rapid convergence time. Exterior gateway protocol or EGP, that is actually used to convey routing information in between autonomous system, two different autonomous systems. So that decouple from IGP, it means your routing policy within the AS and the routing policy and another AS on IGP are two different. So to kind of do routing in between AS, BGP will be on top to kind of select the path based on your policy. As an EGP, we have an option called BGP. The current version is BGP4 or multi-protocol BGP that we have. So why do we need the EGP or accelerated protocol? Obviously, that will scale a large network. It means we have a customer, we have our peer, we have our transit provider. We need to do routing in between all those different entities, right? So this is why we use EGP routing protocol, and that will define the administrative boundary. How the administrative boundary? We have BGP in between my network and my customer network, right? So we have an administrative boundary, and we do routing in between my customer using BGP routing protocol. We have the demarcation between our peer, between our transit and all. We also can implement our business policy using BGP routing protocol. Say the slide that we saw, like a couple of slides before, how we can implement the policy in between AS, that can be done easily using BGP. Okay. BGP is sort of protocol that is very flexible, very reliable in terms of implementing business policy. So if you need to compare interior versus exterior routing protocol, in interior routing protocols, for example, OSPF, ASes, neighbor discovery process is automated. So they normally discover neighbor automatically, except like non-broadcast multi-access network in OSPF. Generally, we trust all those IGP routers because all are under single administrative domain, right? A single administrator has got control to all those routers. Prefix usually go to all IGP routes. Bind routers in one AS together. So all those autonomous system, all those routers within the autonomous system, they bind using a single autonomous system number, right? That carries ISP infrastructure prefix, interior routing protocol. And ISP, they always try to keep the IGP very small, very short and sweet, so that it can rapidly converge and easy for troubleshooting. In exterior routing protocol, on the other hand, we need to specifically configure those peer manually, right? So, and that connects to an outside network that sets the administrative boundary, as I already explained, right? In between two AS, that sets the administrative boundary. This side administered by one administrator, that side administered by other administrator. AS or exterior routing protocol, they actually bind AS together. So, for example, if you consider the internet, how internet has been grouped. So all the AS numbers has built the internet. So that is how we group AS together using exterior routing protocol. Exterior routing protocol, as I said, they carry customer prefix, right? All the customer prefix will be carried via BGP, and BGP works on layer 4, so they can carry heaps of prefix, hundreds of thousands of prefix. Exterior protocol can also carry internal prefixes, right? So within an AS, two routers, they all can carry your external prefix. So for example, if you have POP1 in one AS, and from POP1, if you collect all the customer prefix, that prefix can go other side of your AS via a BGP or exterior protocols, for example, IBGP. EGPs are independent of ISP's network topology. It doesn't matter how your topology has been defined, right? So IGP will ensure based on the topology what path is the best path, and EGP they'll just use the next hop, right? And next hop reachability, it depends on interior gateway protocol or IGP. If you see the hierarchy of all those routing table or routing protocols that we discussed, this is what simplified topology that we have, right? Within all those router, we use OSPF, ASes sort of protocol, and then IBGP among them, and then all the customer prefix in here, external prefix can come on the edge router via BGP, right? And those customer prefix we are not going to redistribute into OSPF. So what we are going to do through IBGP, those prefix will be carried on the other side of the network. So that is what sort of a simplified hierarchical diagram of a service provider network and how routing protocol can be used. Cisco router is very popular. It works on the same, those concept works in the same way on the other vendor routers. So if you see, if you have more than one routing protocol running on the routers, how those routers, how that router select best path if you have, or if the router learn those paths from a multiple routing protocol. So then we have the concept of administrative distance or AD value, right? So connected interfaces has got the lowest AD value, so they will win. Then the second priority will goes to the static route, which AD value is 1. Then enhanced IGRP summary route AD value 5, external BGP AD value 20. So those are the values are predefined in the industry. So those are the AD value. We can change it, but it's recommended not to change it unless we have a complete picture of the topology and the routing protocol. Those are the predefined AD value has been kind of or administrative distance value used by Cisco. So that's why if we have more than one routing protocol running, say for example we have OSPF, we have external BGP, or we have internal BGP. So based on the AD value, your router will select the best path. Make sense? So that's it. That is what the presentation that we have for today. So now we are at the question and answer section. We have a couple of minutes. So if you still have any question, please ask me the question. Otherwise, we have kind of an URL in here where we have the feedback. So we really encourage you to pay us a feedback. This is what the URL that you can use. When you finish the feedback, then it will redirect you to an FTP site. From there, you can download the presentation slides. So if you need to download the presentation slide in PDF format, please finish the feedback, and then it will redirect you to kind of download the presentation slide. Someone raised their hand for a question. Yes, please just write your question on the chat box, then I'll be able to see it and I'll try to answer it. So is there any question? I saw someone was raising a hand. So yep, just write your question on the chat box, and I'll try to answer your question. Well, probably you don't have any question, but yeah, that's all right. So yeah, there's a question. I will send survey from. Thanks for your training. Okay, yeah, that's also good. So if you have any question, you can send us the question via the email. So we have a help desk that runs extended hour, so 9 a.m. to 9 p.m. in Brisbane time. You can send the question to helpdesk@apnic.net, or you can send the question to training@apnic.net. We'll try to answer your question. There's another question. Can I have recording video for this training? Well, we are not releasing any recording as of now, but yeah, we are in the process of doing all those recording, and then we'll try to put those things in the video archive. Just keep your eye on. Probably soon we'll have those video available in the video archive. Then from there you can download it. Make sense? But not now. Probably very soon we'll have it recorded and uploaded to any site. Make sense? So all right. So thank you very much, and hope we can